Hi everyone, thanks for attending my talk. Today I'm going to talk about TPM fail, which is related to some vulnerabilities on trusted platform modules that can actually be exploited to leak cryptographic keys from these secure platforms. My name is Daniel Moghimi. I'm a security researcher, and I've been working as a PhD student on a few topics like microarchitectural attacks, side channels, and applying them to break crypto implementations and Intel SGX. And you can reach out to me on my Twitter, or there are information on my website as well. Before I start my talk, I would like to also thank my collaborators in some of these works, like my advisors Berg Sunar, Nadia Henninger, Thomas Eisenbart, and Jan Wischelmann. Before we dive into the topic of this presentation, which is related to side channel cryptanalysis, we basically motivate on the fact that on traditional cryptanalysis, an attacker try to look at a crypto system, at the input and output of this crypto system, and try to find some flaws that can be used to leak the crypto key by just finding some design flaw and things like that. A good example of this happened 10 years ago on PlayStation 3, that they were using ECDSA not in the proper way. And what happened then was that, so in ECDSA, we have like these fancy equations here that we can compute a signature pair. And here in these equations, there is a nonce that is a secret value that needs to be generated for each signatures uniquely and randomly. And there is a private key here that is the private key for that message. And what happened back then is that the designers of PlayStation 3, they basically used the same nonce for all the messages, and this equation turned to something like this. And when you do that, the problem is that if you just generate two messages and you subtract them from each other, you get a much simpler equation with just one unknown variable, and you can just calculate the private key from this. So this is a huge design issue, and that's what traditional cryptanalysis is about, that people try to find design issue in the actual algorithm or the actual design of some crypto system to break it. But in side channel cryptanalysis, we are not playing the same fair game. We actually have more information about the system. And the idea is that during the execution of a crypto system, we can learn some signal, something like timing channel or other things that can actually be used to perform key recovery in a more efficient way. And there are lots of different types of side channels. For example, there is power attack, electromagnetic attacks, timing attacks, cache attacks. And these attacks, they have a very complicated threat models, because some of them can be conducted on a physical access device scenario. Some of them can only be done in a local attack scenario, like in the cloud, and some of them can also be done remotely. And this actually makes it really complicated for crypto developers to implement an algorithm to be secure against all these different scenarios. So we mentioned that today's talk is about trusted platform module. So just basic, what is trusted platform module? The basic idea is that we know that we cannot really rely on operating system or the hypervisor for root of trust and security, because there are all sorts of attacks that compromise the system software. Like there is rootkits, there are different things, and we know that even sometimes the CPU cannot be trusted, as we have seen by attacks like Meltdown and Spectra. So the idea is we need something like hardware base of root of trust, and we have designed things like trusted platform module, for instance. Trusted platform module is a secure element that is a standard, and it has to support a standard set of functionality. And the other promise of this trusted platform module is that it basically defines a security chip that need to be secure against even some of the physical attacks, like tampering and side channel attacks. And these TPM devices, basically, when you have one of these, you can simply put all your crypto keys or important assets inside this kind of a safe. And if the OS or the cloud provider or any of the software level or even anything that runs basically on your CPU get compromised, they cannot subvert the entire control, and they cannot access to all of the information. So What is inside this security chip or trusted platform module? There is a specific set of functionalities that is defined by trusted computing group and organization. And basically based on this definition, this trusted platform module has to support some secure storage and also some cryptographic functionalities like digital signatures. And we're going to talk about digital signatures more in this talk, and it's important. But in general, these digital signatures can help us to execute signing operations more securely. And nowadays, there are lots of software stacks like the Linux software stack or OpenSSL that they actually support using trusted platform module or TPMs for performing signing operations, whether it's RSA or CDSA. And another important aspect of these digital signatures is that you can actually use them to perform remote attestation of hardware from the other side of the internet. You don't know if another party is running the correct firmware, the correct hardware, and you can use remote attestation to verify some of these promises. Since 2010, Trusted Platform Module version 2 now supports elliptic curve digital signatures and schemes like ECDSA or ECDAA, and these schemes use elliptic curves that are actually more efficient and are actually more popular nowadays. So one thing we mentioned is that, okay, these trusted platform modules, they have some standard and they need to support a set of functionalities. But one thing that we are interested in to know also if these devices actually support any, if this standard supports any implementation standard, like how do we know if these hardware devices, the security chips are actually implemented properly? So TCG expect designers and developers of these products to maintain a security assurance according to common criteria, and the level of assurance they expect is EAL4+. And if you go on the TCG website, you can also find a list of devices that actually have proper certificates. And for instance, in this picture, we see some devices from ST Microelectronics or Nuvoton or Infineon that are listed here. And for example, one thing here we looked at is this is like a picture of ST Microelectronics that I actually took from the laptop that I'm using today for this presentation. And we looked at the data sheet of this chip, and it shows that, okay, this supports resistance against side channel attacks. And we also looked at the evaluation, and here is the link for the evaluation of this TPM chip. And it's also like we looked at through the different part of this evaluation. It says, okay, this is the version that is evaluated, and this is the date that the evaluation has been conducted. And there are some interesting information, like for instance, both the RSA and ECC keys are actually used for endorsement of this device, which is the root security key that is used for these devices. And there is also other things that says, for instance, this device need to maintain security of all the assets inside it. And the list of assets is defined by the protection profile, the user key, or other keys that are stored in the storage. They all need to be protected for the implementation of these devices. And more explicitly, it also says that this evaluation supports side channel attacks and timings attacks and attacks like SPA and DPA. And there's also other information like the standard that it needs to support physical manipulation and physical probing is covered. So we see that basically this says that, okay, this device actually supports mitigation against these side channel attacks. So now the question is, okay, should we just rely on these certificates and say, okay, this is done, this is a secure device or not? So the first thing we wanted to basically test is the simplest test that's also very practical is a timing test, because if we can recover any key from these devices using a timing attack, it's actually very valuable, and it's an attack that is not intrusive. It can even maybe done remotely. So to build a testing tool and measure the timing of these TPM devices, what we did is that we looked at the CPU cycle count, because we realized that most of these TPM devices are implemented on a very low-cost microprocessor that may run like 100 times slower than CPU. So using CPU cycle count is a good way to measure time for these devices without any special equipment or anything. So one of these devices that we looked at initially was called Intel Platform Trust Technology, or Intel FTPM. This Intel FTPM, the idea is that they have implemented the TPM features as it is defined by TCG as a module that runs on the CSME or management engine inside the same die as the CPU. And this management engine also runs its own microprocessor, so it's separate from the CPU. So even if the CPU gets compromised, you cannot really, you are not supposed to have access to that microprocessor, even though if they are on the same die. And this has been around now for a long time, since Haskell, and it's very popular because most computers and laptops nowadays, they can just rely on these if they have an Intel CPU, and they don't need to attach a separate trusted platform module, a dedicated trusted platform module to your motherboard. We did an initial timing test, and we realized that, okay, if we run ECDSA on this TPM, firmware TPM, we see that for different executions of the same ECDSA function with the same private key, the timing operations are actually different for different execution. And here we see a histogram of histogram of a number of signature operations and their timing. So this got kind of our curiosity, like, okay, so we see as timing behavior here, this is interesting, can we do better? So what we did is that we basically implemented a tool to do this timing measurement more precisely. Our tool basically overrides some of the functionality of the Linux kernel stack for TPM. And this functionality, when it's overridden with our tool, we can actually measure the time of the TPM operation as close as possible to the interface of the TPM device. And by doing that, we can get a very high resolution timing of what's actually going on, or if there is anything interesting. And when we did that, we saw that, okay, this Gaussian distribution actually become even more separated, and we see that there are different brackets here in this timing operation that is measured with a root axis. So we use the same key to generate all the signatures, and this actually told us that, okay, if we use the same key to generate all the signatures, the only thing that is changing is the nonce, and that could be the reason that we see this timing behavior. So we looked at the nonces for some of the signatures we generated, and we realized that there is actually a leakage behavior that is directly correlated with the bit length of the nonce. So for example, if we execute this a signature operation, and this is the nonce that is used, we see some timing like this. And if there is like 4-bit window of leading 0 bit at the beginning of the nonce, we see that the timing is much faster. And so we see that for every additional 4-bit window of leading 0 bits at the nonce, the signature is generated much faster. And for instance, if we have like 12 leading 0 bit in a signature, the signature may be slowed, maybe faster, like for more than 3 milliseconds, which is a very high timing behavior that may be even be observable over a network. And here I prepared basically a demo of how such an attack works, that we can collect timing measurements. First, we use a script to generate OpenSSL, generate the ECDSA key using OpenSSL, and then we program the device with this key. So this script runs, we program the device with a new key for ECDSA operation. And if we look at the key, we see that, okay, we have generated a 256-bit ECDSA key, and yeah. And here is the key, the private key starts with the hex value 92 and so on. And then we have another script here that basically uses our tool to measure the time and also run a TPM signing operation. So we use this tool basically to generate signatures and also measure the time of execution of that signature. And when we run this tool, we see that a new entry has been added, that it has some signature pair and some timing values. And if we keep running this script, we see that, okay, another entry has been added. So for our attack, we basically run this script for a while, and here we have also a live histogram of what's happening here. That we see that as we generate these signatures, some of these signatures are faster, and this means that the bit length of the nonce was shorter for those signatures. And this histogram, as we see, is populated with this bit length value, and we see that some of the signatures are faster. And for an attack, we are generally interested for the signatures that are on the left brackets, because we know that they have some bias in their nonce. So this was a vulnerability basically we found on Intel FTPM or Intel PTT. And even though this device has some security guarantees like the FIPS certificate, but it doesn't have any CC evaluation, and it's not listed on Trusted Computing Group website. So we were interested to also see if there are similar vulnerabilities in other TPM devices. So we used our tool to do timing test of a bunch of computers that we had in the lab. These computers, some of them, they just use the Intel FTPM. And when we ran this test on Intel FTPM, almost all of the devices that were using this Intel FTPM were vulnerable to this timing behavior. And then we also found some interesting thing and interesting other timing behaviors on other devices like on Nuvoton and Infineon. But the only other interesting vulnerability we found was on ST microelectronic TPM device that we also earlier showed that it's supposed to be resistant against this attack. And here is basically the histogram we drew for the timing behavior of ST microelectronic, and we see that even though at the first glance it looks like a balanced Gaussian distribution, but we have more samples on the left side, and it actually gave us an idea that, okay, this may also have a timing behavior. So we looked at the nonces again, and we realized that, okay, this is a very similar vulnerability compared to the Intel FTPM ECDSA operation. But this time, instead of for every additional 4-bit window leading 0 bits, we see that for every additional leading 0 bits, for every one leading 0 bits, we see that the timing is faster. And we also looked at that, okay, there is a linear correlation between the bits length of the nonce and the timing. So this again gives us the similar leakage behavior. So far we have just talked about, okay, we have some vulnerabilities on this ECDSA operation of these devices, and this vulnerability tells us some number of bits about the nonce for ECDSA operation. But this information by itself is not useful. We need to use this information to recover something that is more valuable, like the private key for ECDSA. And for this purpose, we basically came up with a systematic attack. And this systematic attack, assuming that the TPM is programmed with a private key, with an unknown private key, we can basically, what we do is that we collect a list of signatures using this TPM device, and these signatures are collected with their timing, and we use the timing basically to filter signatures to a group that has some bias, some non-bias. For instance, we know that all the signatures that are generated in less than X amount of cycle are supposed to be 8 bits short, for instance. And when we have those biases, we basically can use a technical lattice-based attack, and using this lattice-based attack, we can recover the private key. So I'm not going to get into the detail of how lattices work. There are lots of mathematics behind that, and it's beyond the scope of this talk. But the idea is that we can rewrite that ECDSA equation we showed earlier as a simpler equation that has some known values and some unknown values. And then when we replace the known values with simple like variables, we have just this equation that has 2 unknowns. And for these 2 unknowns, we cannot simply calculate any of them, because we need at least one of them to calculate the other. But the reality is we have some information about the value of the nonce, or Ki. And this information tells us the Ki cannot be bigger than some amount, because we know the bit length of Ki for some of these signatures. And this basically resemble a very well-known problem of hidden number problem that was proposed a long time ago, and it can actually efficiently be calculated, and we can efficiently recover the private key from this if we have enough signatures with this quality. And what we did is basically we use this information, we construct a lattice. This lattice is described in a form of a matrix here, and this lattice basically form a problem that is well studied in the lattice-based crypto community. And this problem basically tells us that, okay, we want to solve a shortest vector, and if we solve this problem, we can actually recover the private key. And surprisingly, this problem can be solved in a polynomial time, and there are some algorithms like LLL and BKZ that we can execute on this lattice to recover the private key. And we did that, and it actually worked. And here is also a demo for this attack, basically. So for the same key that we showed earlier, we collected more results. Here we have, for instance, 25,000 signatures that we generated. These signatures, now we can see that, okay, these are the Gaussian distributions, and we are probably more interested in the signatures that are generated faster. So here, if we look at the value 4.7 to the 10 to the 8, these are the signatures that probably have 8 bits of leading 0 bits, because this is the second window here. So we program this value to our tool. We filter all the signatures that are executed that fast. And when we filter these signatures, we realize that there is only 99 signatures out of this 25,000 signatures that they have this quality. And we save these 99 signatures, and then we use another script that we have programmed using Sage. And this script basically randomly picks 60 different signatures from this set of filtered signatures to run the lattice attack. And here we also have the same private key 92 to check as a ground truth to see if our attack works. And if our attack works, this function solve CVP is gonna recover the key. If the key matches the key that we have put here as a ground truth, then the attack works. And here is the simple definition of the lattice in matrix form and running the LLL algorithm in the code. So if we run this, we basically see that, okay, our attack works even when we randomly pick different set of samples. And every time the correct key is recovered. So this was basically an efficient attack. We saw that, okay, running the attack actually doesn't take that much time. The only thing that takes time is collecting those signatures, because depending on the amount of leakage we have, if we have 4-bit leakage or 8-bit leakage, we need to collect different amount of signatures. And we have some numbers in the paper in more detail, but the end result is that you can recover the crypto key very efficiently on both Intel FTPM and ST microelectronic, especially if you have a local access that's very fast, and signature generation may take some time. So after we did this, it was like, okay, we have a almost remote attack on TPM devices, which means that this TPM is even not supposed to leak these keys with a physical attack, but we can already leak these keys from the CPU, because we can measure the timing and leak these ECDSA keys. But can we do these attacks on a real remote like network or remote timing attack, like as is known by the community, like in the wild? So what we looked at is, okay, these TPM devices, they are running with a very slow frequency, and because of that, the timing difference for every of these short signatures, the different brackets, is different. For instance, for the Intel FTPM, the time difference for each of those group of peaks we saw is like about more than 1 millisecond, which means that if you have like 12 bit of 0 at 1 nonce, that signature is going to be executed like for more than 3 seconds faster. And that means that on most local networks or even some internet networks, this can be kind of observed. And for instance, here I have like the round trip time on my local network of pinging another device in my local network, and we see that the time it takes to do a round trip is like less than a millisecond, which means if I have a leakage that is like 3 millisecond delay, this is something that probably can be observed easily over even a local network. And even on some remote networks here, if I ping Cloudflare, it takes 20 milliseconds. So maybe this is even observable over online, like an internet network. Well, we didn't do an attack on internet network, but on a local network, we try to see if what is the impact of this attack on a local network. So we picked up an application, a VPN application that actually has the instruction how to use a strong SON VPN to configure it to use TPM for authentication. So when we configured a strong SON VPN to use TPM for authentication, what we realized is, okay, the first handshake is the same. There is a diffie-Hellman key exchange at the first handshake with the server. And then after this diffie-Hellman key exchange, both the client and the server, they both have the shared key for encryption of their packets. But then the client also need to make sure the server is the correct server, so it's not a impersonated server. So then the authentication happens in the next IKE exchange protocol. And then during the next exchange, the VPN server doesn't even have the access to the key, and it's going to ask the TPM device, hey, this is a message, please sign this for me. And then the server asks the TPM device to sign the message, and the TPM device sign the message, and then the server just get the response and send it to the client, and the client can verify that, oh, this server is a legitimate server. And the good thing about using this TPM is that, okay, now even if the server is compromised, nobody can have access to that private key. So nobody can impersonate the VPN server, the role of the VPN server, basically. But the bad thing about this is that if we have vulnerability on the TPM device, then every time there is a handshake, you can measure the time. So here what we did is that after the second handshake, we just drop the connection and we repeat this operation again, and we collect lots of timing measurement. After doing that, we again applied the same attack that we explained as our local attack as the root adversary, and with the local attack, with the remote attack, we again managed to recover the private key from a VPN server. And for this attack, we needed like about 44,000 handshakes with the VPN server that we configured on a local network. That takes about like 5 hours to collect this amount of signature, and the attack is also about 60% of the times is successful with this network. And here also we see a comparison of different histograms that we generated for this Intel TPM vulnerability, and we see that for system level adversary, the leakage is almost as clean as if we already know the BIOS. There is no interesting statistics behind it. It's just clean leakage. And for the remote attacks, the leakage is noisier, and the remote attack with VPN protocol even is more noisier. But what is clear is that there is still possibility to leak the key, and we actually showed that you can recover the private key over a network. So you may be surprised, okay, why are there such problems on these TPM devices? And this is not actually the first time that we show such a vulnerability on some deployed crypto products. Like around 2 years ago, we showed that another product that uses these signature schemes, like a signature scheme called EPID that also use elliptic curve, actually has this leakage. And we show that on Intel SGX product, their coating enclave that is used as part of the remote attestation is actually vulnerable. And using a cache attack, we could actually recover the private key for remote attestation. So these why is it so easy to break this crypto implementation when it comes to side channel attack? The reason is that implementing this crypto implementation is really hard. It's really hard to implement them to be resistant against all sorts of different side channel attacks. If we look at the ECDSA, for instance, as we talked a lot about ECDSA, is that there is a simple equation here that, okay, this is the ECDSA signing operation, but in reality, there is more going on in the back, and implementing this is much more complicated than it seems. So for an elliptic curve, we have like a curve. This is called the elliptic curve, and it's defined that, okay, this is a secure curve. And then we have two primitive operations. One operation is called double, that after we double a point, point, we get another point on the same curve here. And again, for another operation called add, we add 2 points together and we pass a line through these 2 points and we get another point here mirrored down there. And these are the two basic operations, but using these two basic operations, we can implement more complicated operations. For instance, during the CDS assigning operation, one complicated operation is the scalar multiplication. And we can implement a scalar multiplication using a series of double and add operation, as we can see that, for instance, multiplying 3, 7, 23 different numbers with a point can be done using this add and double operation. And this gives us a simple algorithm. We can use this to implement the CDSA. But there is not a single implementation of this algorithm, and we see that this algorithm has behavior depending on the key bits. And there are so many other algorithms. There is like double add algorithm that we showed. There is Montgomery double add. There are like a sliding window, fixed window. So there are so many different ways to implement the same functionality that is part of this CDSA signature. And in our case, the showcase we showed in fixed window in Intel TPM, it was actually a fixed window implementation that was leaking for every 4-bit window. But if you are designing crypto system, this is very difficult because you are not sure what is the threat model. You may implement this crypto system to run on a cloud, but then later on you may use the same code to run it on an airplane, and people have told you not to implement your own crypto, so you just copy paste the same crypto library from one design to another. And this makes it really difficult. And a while back, we actually were curious, okay, how can we find these leakages automatically instead of trying to attack every specific implementation on different platforms? And one thing we came up with here is that, okay, all these software-related side channel leakages, they have some characteristics. They either happen due to a secret dependent control flow, like when you do a loop or if a statement that depends on the key bit, or when you try to do a memory access depending on the key bits, like when we see that in some block ciphers like AES, that they have something called SBox. And in some rare cases, there are also some instructions that they leak some value about the input, like on some ARM CPUs, for instance. This has been reported. But the idea is that, okay, we want to have an automatic tool and we want to apply this understanding to recover these leakages from a software perspective without even caring what computer or what threat model we are running to. So in reality, the way our tool, which we call it macro work, is that, so in practice, an attacker learn about the execution time, the memory usage behavior, the cache access pattern. But in theory, in the principle, what happens is that the attacker learns something about how many instructions are executed, or what branches have been taken, or what is the memory access pattern of the software. And so we said, okay, we're going to try to have a more tight model, and we just look at the principle of why the leakage happened. So we came up with this tool, and the idea is we generate a set of random test case, and we feed these random test cases to the implementation of a crypto operation. And while we are feeding these test cases, we also generate the execution trace of this crypto operation. And then one way to see if there is a leakage, we show that we can check the difference between the traces for the same for different inputs. And another way, we also use mutual information. We said for every instruction that has been executed during the execution of this crypto system with different inputs, we're going to calculate a mutual information score. And we say, we look at if this mutual information is positive. If there is a score associated with the instruction, it means that that instruction was involved with the operation that took different inputs or different amount of execution, and that actually tells us there is a relationship between the leakage and that instruction. So using that, we can actually also look at which instructions are leaky. And our tool, the way it works is that first we generate these traces and we do some tweaks to the generation during the execution. We use something like Intel pin tool to do binary instrumentation, so it can work on binary software that we don't have access to the source code. And then we do some pre-processing of the trace, because some of these operations, like they have different address space because of ASLR or because of memory allocation. So we try to normalize the trace so we don't have false positive. And we also apply some leakage granularity, like you may be interested in cache level attack or page level attacks and things like that. And then we applied the analysis that we mentioned. So we had this tool, but apparently the vendors didn't have access to such a tool, or they didn't care enough to use it. And this is basically the responsible disclosure we had with ST Microelectronic. We reported this vulnerability to them about a year ago, and we had lots of exchanges with them to help them to update the firmware for this device and fix these devices. And later on, some vendors like HP and Lenovo issued some firmware updates to fix this issue. For Intel, we also had a responsible disclosure that was a little bit longer, about 9 months, and then similarly we reported this issue. And what's interesting is after we reported this issue, they told us that the reason they had this vulnerability was that they were using an outdated version of library. And this also matches our previous reports, because we already reported similar vulnerabilities in Intel IPP, which is an official crypto library by Intel, as part of our study of the MicroWalk tool. And we already reported these vulnerabilities like 2 years before, like in 2018, but later on again, the same vulnerability appeared in another product, another consumer product actually. And that's actually an interesting thing, that sometimes the knowledge you gain from cache attacks and analyzing software leakages can be transferred to a totally different type of side channel, and with even more bad consequence on the products. This is my talk, and here are some links about our tool, about this attack, and also this paper will appear also at Usenix Security Symposium, which happens soon right after the Black Hat.
Yeah, so I have one question in the chat window that asks, from what I can remember, TPMs should be generating key materials with an artificial response time to prevent this type of timing attack. Your results show this is not true, but is that a problem in the standard or the TPM vendors? I believe that the TPM standard itself doesn't impose how the vendors are supposed to implement the actual TPM hardware, but the CC certification, when it's at level 4 or 5, expect the TPM vendors to have some mitigation. So I don't know if, I hope that clarified the answer for that. Any other question? So I don't see more questions, but I would like to again thank the audience for listening to my talk. Yeah.